A 20,000-ton freight train hits a 2% grade somewhere in the Rockies. The driver pushes the throttle wide open. The engine responds with all 4,400 horsepower it has. The wheels spin faster. The train doesn't speed up. More power makes it worse. One of the most powerful machines ever built, stopped dead by a slope that rises just 2 meters over 100. You'd walk up it without breaking stride. And the reason has almost nothing to do with the engine. Here's what engineers decided to do about it. They didn't fix the train. They moved the mountain. The Gotthard Base Tunnel in Switzerland runs 57 kilometers through solid rock. It took 17 years to build and cost over $12 billion. The reason it exists isn't to save time. It exists because the gradient above it was too steep for heavy freight trains. In Norway, the Bergen Line spirals through the same mountain multiple times, looping back on itself just to gain height gradually enough that the locomotives can handle it. Look at that route on a map, and it looks insane. Tracks snaking around hillsides, following river valleys for miles in the wrong direction, crossing enormous viaducts over gaps that would have been cheaper to go around if going around didn't mean going uphill. This isn't rare. This is standard railway engineering. 2 centuries of it. The most expensive infrastructure projects on Earth, built not to cross obstacles, but to avoid a gentle slope. Multi-kilometer tunnels drilled through granite because the math said digging was cheaper than building a track steep enough that trains would stall on it. Bridges spanning entire valleys because the valley floor offered a flatter path than the ridge above. Every one of those tunnels, every spiral, every bridge that seems dramatically overbuilt is an admission. The most powerful freight machines on the planet cannot handle what your car doesn't even register. And the obvious fix, just build a stronger engine, is exactly the wrong answer. Because that's the first thing everyone suggests. More horsepower. A bigger engine. If the train can't climb, give it more power until it can. Locomotive manufacturers tried exactly that for decades. They built engines with 6,000 horsepower, then 8,000. It didn't matter. The moment a train hits a grade steep enough, something happens that makes raw power irrelevant. The wheels keep turning. The engine keeps producing full output, but the train barely moves. More throttle actually makes it worse. The wheels spin faster, but the speed doesn't change. All that extra horsepower just converts into heat and noise. You've felt this yourself. A winter morning, ice on the road, you press the accelerator and the engine screams. The tires spin. The car crawls. Pushing harder doesn't help. It makes you lose what little grip you had. That's not an analogy. That's the same physics. Engineers call it wheel slip, and it means the engine was never the bottleneck. A locomotive could produce 1,000,000 horsepower, and it wouldn't matter once adhesion breaks. The power has nowhere to go. It's like pouring water into a glass with no bottom. So if the limit isn't the engine, something else is deciding how much force actually reaches the rail. And that something is embarrassingly small. The contact patch, the spot where a steel wheel actually touches a steel rail. Each one is roughly the size of a coin. A typical locomotive has 4 axles, 8 wheels, and the total area where all that power transfers to the track is barely larger than the palm of your hand. That's it. That's the bottleneck. Thousands of tons of freight, 4,400 horsepower, an engine burning diesel at full output, and all of it funnels through a few square centimeters of steel pressing against more steel. When gravity starts pulling the train backward on a grade, those tiny patches are the only thing fighting back. Once the force exceeds what those patches can grip, the wheels spin. Doesn't matter what the engine is doing. But here's the part that breaks everyone's intuition. If you pulled those steel wheels off and bolted on giant rubber tires instead, the exact same locomotive with the exact same engine could climb dramatically steeper hills. Immediately. No extra power needed. Rubber deforms. When a rubber tire presses against a surface, it squashes slightly, spreading out, gripping. That deformation creates enormous friction. Steel doesn't do that. Steel is so rigid that it barely touches the rail at all. The contact stays tiny, the grip stays minimal, and the train stays stuck on any grade steep enough to overwhelm those coin-sized patches. So engineers chose the material with worse grip, deliberately, knowing it would make hills nearly impossible, knowing it would force them to dig tunnels and build bridges for the next 200 years. And they'd do it again. Because the reason they chose steel is the entire point. Steel wheels don't grip. That's the flaw. But steel wheels also don't drag. And that's the advantage that built an entire industry. Every time a rubber tire rolls down a highway, it squashes against the surface. The rubber deforms, spreads, recovers, deforms again, thousands of times per mile. That constant squashing takes energy. A significant chunk of a truck's engine power on flat ground isn't moving cargo forward. It's being eaten alive by the tires fighting the road. A fully loaded semi on a highway is burning fuel just to keep its rubber rolling, before you even factor in wind or weight or hills. Steel doesn't have that problem. A steel wheel on a steel rail barely deforms at all. It rolls almost free. The energy that a rubber tire wastes fighting the road surface simply doesn't disappear on rail. It stays available, which means almost all of a locomotive's power goes directly into one thing: pulling cargo. That's why a single locomotive can haul 200 freight wagons stretching over 3 kilometers. A highway truck with a comparable engine moves 1 trailer, maybe 2. The locomotive moves 100 times the load on a fraction of the fuel because it's not wasting energy on grip it doesn't have. That's the trade-off. Low friction means almost no wasted energy on flat ground, which means absurd hauling capacity, which means the most efficient freight system humans have ever built. But low friction also means almost no grip on a slope, which means a 2% grade can stop 20,000 tons cold. You can't have one without the other. The same property that lets a train move impossible loads is the same property that makes it helpless on a hill your car wouldn't notice. Engineers didn't stumble into this. They chose it. Nearly 2 centuries ago, they picked efficiency over grip and never looked back. But a problem that can't be engineered away still has to be managed. And the primary solution has been hiding under locomotives for over 100 years. Sand. Hidden beneath nearly every modern locomotive are sandboxes filled with fine, dry sand. When sensors detect the first sign of wheel slip, compressed air blasts a precise amount directly onto the rail, right in front of the wheels. The friction spikes instantly. Those coin-sized contact patches suddenly grip just enough to keep pulling. That's the fix. Not a bigger engine, not better wheels. Sand. It's been the primary solution for over 100 years. The technology has improved. Modern systems use electronic sensors, automated delivery, calibrated flow rates, but the core idea hasn't changed since the steam era. Pour grit between steel and hope it's enough. If you've ever heard a faint scraping sound while a train accelerates out of a station or struggles up a grade, that's sand hitting rail. Most passengers never notice. Most never realize the train beneath them was losing grip, and a century-old Band-Aid caught it. But sand buys time. It doesn't solve the physics. On steep enough grades, gravity still overwhelms those contact patches, sand or no sand, which is why engineers eventually abandoned friction altogether and built something that looks like it was pulled from the inside of a clock. Rack railways. A toothed rail bolted between the 2 running rails, and a matching gear underneath the locomotive that meshes into it like a zipper. The train doesn't rely on friction anymore. It climbs mechanically, tooth by tooth, like a giant ladder laid against the mountainside. It works. Spectacularly. The Pilatus Railway in Switzerland climbs a 48% grade, nearly half a meter of rise for every meter of track. A conventional train would slide backward before it moved an inch. The rack system doesn't care. Grip is irrelevant when the gear is physically locked into the rail. Engineers eliminated the friction problem entirely, but they also eliminated everything that makes trains useful. Rack railways are slow. The Pilatus line tops out at around 9 kilometers per hour. They're expensive to maintain because every tooth in that rail takes mechanical stress that smooth rail never does. And they can't handle the volume. You're not running 200 freight wagons over a toothed rail at walking speed. The economics collapse immediately. So rack railways exist in the Alps, on tourist lines, in a handful of mountain applications where no alternative works. For the 99% of rail that actually moves freight and passengers, the gradient problem just sits there, unsolved. And unsolved problems that last 2 centuries tend to reshape the world around them. This is what 2 centuries of an unsolved physics problem look like from 30,000 feet. Pull up a map of industrial England. The factories, the mills, the cities that powered the British Empire, Manchester, Leeds, Sheffield, Birmingham. They didn't end up where they are by accident. They grew where the terrain let railways reach them without climbing. Valleys, river basins, flat corridors between mountain ranges. The railroad didn't follow industry. Industry followed the railroad, and the railroad followed the gradient. The same pattern repeats everywhere. In the United States, the Transcontinental Railroad didn't cross the Rockies where the route was shortest. It crossed where the grades were manageable. Cities like Cheyenne, Wyoming exist specifically because the railroad needed a stop at the right elevation. The town was built for the gradient, not the other way around. Ports grew where rail could reach the coast without climbing. Distribution hubs clustered where the terrain stayed flat enough for heavy freight. 200 years of economic geography shaped by coin-sized contact patches. And it's still happening. Right now, Japan's Chuo Shinkansen maglev line, designed to hit 500 kilometers per hour, is being routed through the Japanese Alps using a tunnel over 25 kilometers long. Not because tunneling is easy, because the surface gradients would slow a train that's supposed to be the fastest in the world. Europe's high-speed rail network still routes around hills that a highway cuts straight through. Every new line, every billion-dollar infrastructure project still bends to the same constraint that stopped that freight train on a 2% grade in the opening of this video. The physics haven't changed. The friction limit hasn't changed. Steel on steel still grips like leather shoes on ice. The only thing that's changed is how much money we spend building around it. And that brings us back to where we started. Every tunnel, every viaduct, every track that snakes through a valley instead of cutting over the ridge. That's not engineering ambition. That's a debt payment. 2 centuries ago, engineers made a bet. Low friction would move more cargo than high grip ever could. Steel wheels on steel rails, barely any contact, barely any drag, and because of that, barely any wasted energy. One locomotive pulling what hundreds of trucks can't. The most efficient freight system humans have ever built, born from a deliberate sacrifice. The bill for that bet comes due on every hill. A 2% grade stops 20,000 tons cold. Sand buys a few moments of grip. Rack railways work but can't scale. So the world adapted the only way it could. Dig through the mountain, bridge the valley, add 50 kilometers of track to avoid 2 kilometers of climb. Build cities where the ground stays flat. Route a $100 billion maglev line through a 25-kilometer tunnel because the surface is too steep for a train that's supposed to be the fastest on Earth. The physics haven't changed since the 1800s. The friction limit hasn't improved. Steel still grips like leather shoes on ice. The only thing that's changed is how much we're willing to spend building around a problem we chose to have. And every time a train disappears into a mountainside, that's the sound of the world still paying.